In this video, we discussed the chemistry of the alpha carbon of esters. When ethyl acetate reacts with sodium ethoxide, it undergoes a condensation reaction. After acidification, the product is a beta-keto ester. If we look closely to the reaction, one of the two ester molecules loses an alpha hydrogen, while the second molecule loses an ethoxide. Similar to the aldol condensation reaction, we are going to deprotonate the alpha carbon by use of a base. Different than in the aldol condensation reactions, we have the family of carboxylic acid derivatives that will undergo substitution reaction. We need to recall that during the aldol condensation, we added the nucleophile to a carbonyl, producing a tetrahedral anion. Nucleophilic additions to aldehydes and ketones produce the tetrahedral intermediate that needs to be quenched with a small amount of acid. And we have seen that reaction during the reduction of aldehydes and ketones and during the Grignard reaction. As we have discussed in the chapter of carboxylic acids, when you add to the carbonyl of a carboxylic acid derivative, you form an intermediate tetrahedral, and the leaving group will be the weakest base. Let's summarize. You will add the nucleophile to the carbonyl. We are going to create an intermediate tetrahedral. The carbonyl is going to reform, and when it does, the leaving group will be Y, the weakest base. The first step of a Claisen condensation resembles that of an aldol condensation. A toxide ion abstracts an alpha proton from the ester. Although the alpha protons of an ester are not as acidic as those of aldehydes and ketones, the enolates anion that forms is stabilized by resonance in a similar way. We can push electrons from the alpha carbon to the oxygen. Once we have created an enolate in some of the esters, that can serve as the nucleophile to add to the second molecule of ester. When the carbanion adds to the carbonyl of the second mole of ester, we are going to form a tetrahedral intermediate. It is at this point that the Claisen condensation and the aldol addition differ. When the tetrahedral collapses, it leads to substitution. Although the products of this second step are a beta-keto ester and a toxide ion, all of the equilibria up to this point have been unfavorable. Very little product will be formed if this were the very last step. The fact is that the ethoxide leaving group is a strong base to remove the alpha hydrogen from the dicarbonyl product form. One easy way to prevent deprotonation of the alpha hydrogen left is by addition of a small amount of acid to produce ethanol from ethoxide. Without the use of acid to quench the reaction, the equilibrium favors the formation of a new carbanion. If we add acid, we will neutralize the ethoxide form that can be distilled as ethanol. The beta-keto ester product can be used to synthesize a ketone after decarboxylation, as we have described in a previous video.